to finish out this chapter, let's just go ahead and work some additional examples, kind of encompassing everything we've covered. Hopefully this gets you guys more comfortable with the overall concepts and everything else that we've done in this section. So the first example, suppose I have reactant A in equilibrium with product B. At equilibrium, a mixture contained 1 molar A and 10 molar B. What is your Kc value? Then, if I add 2 molar A to this system, what happens? First, let's see, 1 molar A and 10 molar B. My Kc expression for this would be the concentration of B divided by the concentration of A. Nothing is, there's no exponents because there's no coefficients in the original reaction, so it's just concentration of B divided by concentration of A. I'm told that at equilibrium, B has a concentration of 10 molar, and A has a concentration of 1 molar. So my Kc value here is 10.0. If I add 2 molar A to the system, what happens? Well, I've got A in equilibrium with B. Now I have 3 molar A and 10 molar B. It's going to react some of that A to form some B and produce some B. At equilibrium, I will have 3 minus x, 10.00 plus x. We will calculate our reaction coefficient here. So because we're not at equilibrium anymore, I want to go ahead and calculate the reaction coefficient and see how does this compare. Concentration of, that should be B over A. I apologize. Now, I don't remember if we've done the 5% rule. I think the 5% rule comes in the very next chapter. I always forget when that comes. But for the 5% rule, basically what we're going to assume is that x is really, really small, and we're going to ignore it. You cannot do that in most of this chapter. Most of the time you're going to have to solve a quadratic, but I don't want to solve a quadratic right now. It doesn't sound fun. So I'm just going to assume that x is really, really small, ignore it, and compare the 10 divided by 3, which gives me a value of 3.33. The point of this is that, remember, we've got Kc, and we want to compare where Kc is to Qc. Kc has a value of 10. My Qc has a value of approximately 3.3, because I did ignore those x's, but approximately 3.3. So Qc is less than Kc, which means, as we would predict based on this reaction, the reaction will react to produce more B until it reestablishes that equilibrium. Now, you could have done this reaction as well by looking at it and just saying, well, if you've got A in equilibrium with B, and we increase the concentration of A, I expect to form more B. Le Chatelier's principle. Completely valid, but you can also do that with math. For the equation, 2 moles of SO2 reacting with 1 mole of O2 in equilibrium with 2 moles of SO3. Everything's in the gas phase. Kc is 278 at 25 degrees C. I want to calculate Kc values for the following reactions. SO2 gas plus a half of O2 gas in equilibrium with SO3 gas. This reaction has been divided by 2, or better yet, multiplied by 1/2. Kc prime is equal to Kc times 1/2, 278 to the 1/2, or 16.7. 2 moles of SO3 gas in equilibrium with 2 moles of SO2 and 1 mole of O2 gas. This reaction has been reversed. Kc prime is equal to the inverse of Kc, because the reaction's been reversed. 1 divided by 278, 3.60 times 10 to the minus third. And calculate Kp for 2 moles of SO2 gas plus 1 mole of O2 gas, giving me 2 moles of SO3 gas. Change in N. I have 2 moles of gas in my product, 3 moles of gas in my reactant, gives me a -1 value. Kp equals Kc times RT raised to the change in N. This equals 278 times the product of 0.08206 liter atmosphere per mole K times my temperature. This is in Kelvin, so 25 degrees C, 298 K. And this RT quantity is raised to the -1, not the 278, just the R and T. Gives me an overall value of 11.4. Find Kc for the reaction 2NO gas plus O2 gas in equilibrium with 2NO2 if I'm given that Kp equals 2.2 times 10 to the 12th at 25 degrees C. So again, we know that Kp equals Kc times RT raised to the change in N. In this reaction, I have 3 mole of gas and 2 mole of gas. So change in N, 2 minus 3 gives me a -1. I'm going to rearrange this equation to solve for Kc. I find Kc is equal to Kp over RT raised to the change in N. This is the same as 2.2 times 10 to the 12th divided by 0.08206 liter atmosphere per mole K times 298 K and that product is raised to a -1. Solve this out, and I get 5.38 times 10 to the -11. But I do need 2 sig figs because this only has 2 sig figs. So I'm going to round this to 5.4 times 10 to the -11. The following boxes represent reactions of the type A in equilibrium with B at equilibrium. In which of the following is Kc equal to 2? Well, our A is the little red dots, our B is the little black dots. So if I've got A in equilibrium with B, and it's equal to 2 for Kc. Here I've got a 1-to-1 ratio. That's not going to do it. Here I've got a 3-to-6, or better yet, 1-to-2 ratio. That's going to do it. And here I've got a 6-to-3, or better yet, 2-to-1 ratio. What I mean by that is A to B, by the way. And I know B is my product. I want Kc equal to 2, which means my ratio needs to be 1-to-2. 2 times more of my product than I have of my reactant. It is reaction 1. Okay. The equilibrium constant is given for the 2 reactions below. Determine the value of the missing equilibrium constant. So a little bit of Hess's law coming into here. We've got an equilibrium constant here, an equilibrium constant here. We're trying to find this one. So this is my target reaction. I want to manipulate the other 2 reactions to add up to my target reaction. So comparing them, what I see is that this first reaction, A and 2B, okay, A is not my target reaction at all, but B is. B is in my target reaction. AB2 is. AB2 is my target reaction. AB2 is actually on the reactant side, though. So I'm going to flip this reaction around. Looking at the second, or the bottom reaction, A, not in my overall reaction, so that must cancel out. B B is in my reaction. Somehow that's got to cancel out to equal just one of them, though. And AB3 is in my reaction, and it's on the product side as it is here. So I'm going to leave this reaction as is. Let's go ahead and flip around the first reaction. AB squared, and that's a gas phase, in equilibrium with A gas plus 2B gas. The third reaction, second reaction is what I'm trying to find. The third reaction I'm going to leave as is. A gas plus 3B gas in equilibrium with AB3 gas. My A's cancel out. My 2B cancels out with 2 of my B's here, leaving me 1 B behind. And I get AB2 gas plus B gas in equilibrium with AB3 gas. So that is correct. That's what I'm trying to find. Now, how do I manipulate these values, though? Well, the first reaction I flipped. When you flip a reaction, you're going to take the inverse of that reaction. So this reaction, Kc prime, is going to be the inverse, or 1 divided by 59. The third reaction stayed the same. So Kc prime, we'll call this Kc double prime. This stays the same, 478. But now I'm adding 2 reactions together. Remember, when I add 2 reactions together, I multiply their Kc values. So for this, we'll call this Kc triple prime for this guy. This equals Kc prime times Kc double prime, or 1 over 59 times 478. Gives me a value of 8.1. And our answer is C. So we can pull things in we've seen before. You guys need to be comfortable with this. Changing the equations around, flipping between Kp and Kc, manipulating the equations with things such as Hess's law. All of these things should be comfortable, and you should be able to do them pretty quickly. Let's look at Le Chatelier's principle again. The reaction, 2 moles of SO2 gas react with 1 mole of O2 gas to produce 2 moles of SO3 gas. Delta H for this reaction is negative 198 kilojoules at equilibrium. How will each of the following changes affect the equilibrium concentration of each gas once the equilibrium is reestablished? Well, first, this is a negative value here, which means this is exothermic. So I've got 2 moles of SO2 gas plus 1 mole of O2 gas in equilibrium with 2 moles of SO3 gas plus heat. What if I add O2 to the container? I'm increase the reactant, so more product. Or it's going to move to the right. If I remove SO3, more product. It's got to make more of it. It's going to move to the right. What if I compress the gases? I have 3 moles of gas over here, 2 moles of gas over here. Compressing, more product. It's going to move to the right. What if I cool the container? Cooling it is going to remove the heat. It's an exothermic reaction, so cooling it will cause more product to form. What if I double the volume of the container? This is the same as decompressing. It's going to shift to the left or form more reactant. If I warm the mixture, that's adding heat. It's going to move to the move to the left or form more reactant. What if I add helium? Helium is non-participating. So no effect. And if I add a catalyst, no change, because catalysts are not going to affect the overall reaction. Okay. At 35 degrees C, the Kc value is equal to 1.6 times 10 negative fifth. That should be a C. In an experiment in which 1 mole of NaCl is placed in a 2-liter flask, what are the equilibrium concentrations? And it gives me the reaction here. So I've got 1 mole in a 2-liter flask, which means that my concentration is 0.5 molar. So I start out with a 0.5 molar NaCl and no mention of NO or Cl2, which means I assume that I start with none of those. 2 moles of NaCl react to form 2 moles of NO and 1 mole of Cl2. At equilibrium, 0.50 minus 2x, 2x, and x. Write out your Kc expression. Your Kc expression is NO quantity squared, or concentration of NO quantity squared, times concentration of Cl2 divided by concentration of NaCl squared. Plug in what I have from the table itself. Concentration of NO at equilibrium is 2x squared. Concentration of Cl2 is x. And concentration of NaCl is 0.50 minus 2x. Now again, I don't think I've actually taught you the 5% rule yet. I think I'm pretty sure it comes in the next chapter. I don't know. It throws me off. But the 5% rule is a rule we're going to follow where we basically assume that x is a really small value. So when we subtract it from something, we can kind of ignore it. And we assume that if it's less than 5% of the original sample, it's safe to ignore it. What it does is it simplifies the math for me. This quantity should be squared. It simplifies the math a lot. So I can kind of ignore that minus 2x down there and rearrange this equation so that it would be 2x squared is the same as 4x squared, but it's 2x squared times x, 4x cubed, divided by 0.50 squared. So I'm ignoring that minus 2x squared part. And again, you will cover the 5% rule very soon. In the very next chapter, I believe. I know it's coming. But just trust me that we're going to ignore that x right now. You can't always ignore the x, but sometimes you can, and it just makes the math easier to deal with quadratic. When I do this, I solve this, and this becomes 1.6 times 10 to the minus fifth. Go ahead and isolate this equation to solve for x directly. 1.6 times 10 to the minus fifth times 0.50 squared divided by 4 is equal to x cubed. Solve for x, and x becomes 1.0 times 10 to the minus 2, and x does represent molar. With that information, I know my equilibrium concentration of Cl2 is equal to 1.0 times 10 to the minus 2 molar. I know my equilibrium concentration of NO is equal to 2x, so 2.0 times 10 to the minus 2 molar. And my equilibrium concentration of NaCl is equal to 0.50 minus 2x, or 0.48 molar. Okay. Reaction mixture at 175 K initially contains 522 torr of NO and 421 torr of O2. At equilibrium, the total pressure of the reaction vessel is 748 torr. What is Kp at this temperature? First thing I need to do is figure out my pressures in atmospheres, because I'm looking at Kp, this is going to be an atmosphere. So let's go ahead and find our pressure of NO, our pressure of O2, and our total pressure at equilibrium of in atmospheres instead of torr. So the pressure of NO initially was 522 torr. Convert that to atmosphere. And that gives me 0.687. Too many R's. That is my initial pressure. I'm going to do the same thing with O2. My O2 initial was 421 torr. Which is equal to 0.544 torr, or 544 atmosphere. And initially, I don't have any NO2 present. 2 moles of NO react, so minus 2x, with 1 mole of O2 minus x, and form 2 moles of NO2 plus 2x. At equilibrium, I have 0.687 minus 2x, 0.554 minus x, and 2x. Now, my Kp for this, my Kp expression, remember Kp is equal to the partial pressure of this substance at equilibrium. So the partial pressure of NO2 squared divided by the partial pressure of NO squared times the partial pressure of O2. And these are at equilibrium. I know their initial, and I know that this is their equilibrium. But I also know that the pressure total at equilibrium is equal to 748 torr. Which is the same as 0.984 atmospheres. I know the total pressure of the system at equilibrium has to be a summation of all of these. These add up to the total pressure of the system at equilibrium. So P total at equilibrium will be equal to 0.687 minus 2x plus 0.554 minus x plus 2x. And that has to equal 0.984 atmosphere. Why? Because this is the total pressure of the system. These three gases add to that total pressure. So I'm going to solve this through. This gives me 1.241 minus x equal to 0.984. So I'm getting all, variables together the best I can. Basically simplifying one side, and that equals 0.984. Solve for x. Negative x is equal to negative 0.257. And so x is equal to 0.257. Now I can go ahead and plug that in here. And then into my Kp expression. So this was equal to the partial pressure of NO2 at equilibrium, which is 2x squared, divided by the partial pressure of NO2 squared, 0.687, minus 2x, quantity squared, times 0.554 minus x. Plug in the values we actually know. Kp is equal to 2 times 0.257, because I know the value of x now, quantity squared, divided by 0.687 minus 2x, which is equal to 0.173, that quantity is squared, and 0.554 minus 0.257 equals 0.297. I find my Kp for this to be 29.7. So a little bit of manipulation there, remembering that your partial pressures have to add up to your total pressure of your system. That's from Dalton's law, from Gen Chem 1, from gas laws. But combining a lot of concepts you guys know, but I promise you know how to do all these parts. Once I was able to figure out the value of x, I was able to quickly calculate Kp. At a particular temperature, K equals 3.75 for this reaction. If all four gases had initial concentrations of 0.8 molar, 0.8000 molar specifically for sig figs, calculate the equilibrium concentrations of the gases. So I know that we have 0.800, 0.800, 0.800, and 0.800. I know that's my initial. My change would be minus x and minus X for the reactants because there's 1 mole of each, plus X and plus X for my products because there's 1 mole of each. At equilibrium, 0.800 minus X for SO2, 0.800 minus X for NO2, 0.800 plus X for SO3, and 0.800 plus X for NO. Write out your Kc expression. Kc is equal to the concentration of SO3 times the concentration of NO, divided by the concentration of SO2 times the concentration of NO2. Substitute in the values we know from our equilibrium or from our ice table. Kc is equal 0.800 minus X times 0.00 minus X. Those should be plus X because they're products, divided by 0.00 minus X times 0.00 minus X, and this equals 3.75. What I want you to recognize here is these are perfect squares. This is the same as saying 0.800 plus X squared divided by 0.800 minus X quantity squared, and this equals 3.75. Because it's perfect squares, it's easy to solve. Take the squares of both sides. So the square root of 3.75 equal to the square root 0.800 plus X divided by quantity squared divided by 0.800 minus X quantity squared. And I wrote this down wrong, so let's see. Square root of 3.75 is 1.94. This equals 0.800 plus X divided by 0.800 minus X. Now I'm going to go ahead and simplify this down. So I've got algebraic manipulation. 1.94 times 0.800 minus X equals 0.800, keep reading the plus there, plus X. Distribute this through. I'm just going to take a sec because I did write down the wrong answer before. I had 19.4 because I wrote down 375, not 3.75. So 1.94 times 0.8 gives me 1.552. Move this up here. 1.55 with sig figs minus 1.94x equals 0.800 minus x. Get my variables on one side, my x's on the other. So I'm going to, doesn't matter which side goes to which. I'm going to put my variables on my left side, my integers on my right. So negative 1.94 minus 1, negative 2.94x. And then 0.8 minus 1.55, negative 0.75, solve for x. X is 0.255. That is a molar concentration. And so now what are my equilibrium concentrations? Well, my concentration of SO2 at equilibrium equals my concentration of NO2 at equilibrium. And those will be equal to 0.8 minus 0.255, 0.545 molar. And my concentration of SO3 at equilibrium equals my concentration of NO at equilibrium. And that will be equal to 1.055 molar at equilibrium. Oops. Okay, at 2000 degrees C, Kp equals 0.05 for the reaction shown below. If N2 and O2 gases are placed in a flask at initial pressures of 0.80 atmosphere and 0.20 atmosphere, respectively, what is the partial pressure of NO once the equilibrium has been established? So I've got N2 gas plus O2 gas giving me 2 moles of NO gas, and I'm told that my Kp here is equal to 0.050. I want to know the partial pressure of NO once equilibrium has been established. So let's see, initially my N2 has 0.80 atmosphere and O2 is 0.20 atmosphere, and I don't have any NO to start. N2 is a reactant, so minus X. O2 is a reactant, minus X. There's 1 mole of each one, plus 2X for 2 moles of NO. At equilibrium, 0.80 minus X, 0.20 minus X, and 2X. Write out your Kp expression. Kp will be equal to the partial pressure of NO squared divided by the partial pressure of N2 times the partial pressure of O2. And write in what we know from our table. We know at equilibrium the partial pressure of NO will be 2X, that quantity will be squared. Partial pressure of N2 will be 0.80 minus X, and the partial pressure of O2 will be 0.20 minus X. One thing I want to specify here is be careful here. I tend to forget those numbers in front. So make sure in your ICE table that if you see a coefficient there, you're writing it down here. It's so easy to forget. And when you forget, all of your math is wrong. So, again, you haven't learned the 5% rule yet, but you're going to learn it soon, and it's a lot easier. I'm going to assume these x's are really, really small, so I can ignore them. Because if they're small and I can ignore them, it makes my math easier. If I ignore them, I have 4x squared divided by 0.80 times 0.20. And this equals 0.050. 0.80 times 0.20, do that math out, and you get 0.16. And now I'm going to solve for x, so 0.05 times 0.016, 4x squared gives me 8. Don't forget your sig figs. 0.0 times 10 to the negative 4. X squared, 2.0 times 10 to the negative 4, and therefore x is equal to 0.014. My x is pretty small, 0.014. Again, you will learn the 5% rule soon, but the 5% rule basically says that if I check this compared to the starting concentration, is it less than 5%? It's a little bit high. Technically, I shouldn't have ignored it. So 0.014 divided by 0.20 times 100% is 7%. It's a little high. I shouldn't have ignored it. But I don't really want to solve the quadratic formula right now, so I'm going to ignore it anyway. We'll talk about that soon, but I'm going to ignore it. What is this all telling me, though? This is telling me that x is equal to 0.014. Well, what do I want? I don't really want x. I want the concentration of NO2 at equilibrium, which is equal to 2x. 2 times 0.014 gives me a concentration of 0.028 atmosphere, or pressure. So the equilibrium pressure, I keep saying concentration because I'm so used to writing KC expressions. I apologize for that. The pressure of NO at equilibrium is equal to 0.028 atmospheres. Last example, silver sulfate dissolves in water with a Kc value equal to 1.1 times 10 negative fifth at 298 K. A 1.5 liter solution contains 6.55 grams of dissolved silver sulfate. If additional solid silver sulfate is added to the solution, will this dissolve? Let's check. It's telling me I have silver. Okay, let's see. 1.5 liter solution, and I've got 6.55 grams of dissolved silver sulfate. So how much silver do I have? Silver ion, I've got 6.55 grams of Ag2SO4. Convert that to moles. Silver sulfate has a molar mass of 311.80 grams. And I want concentration of silver, not per se concentration of silver sulfate. There's 2 moles of silver ion for every 1 mole of silver sulfate. This will give me moles. I really need concentration because I'm dealing with an ice table here. So 1 divided by 1.5 liters gives me 0.028 molar silver ions. How many sulfate ions do I have? Same process, 6.55 grams of silver sulfate. 1 mole of silver sulfate contains 311.8 grams of silver sulfate. Keep forgetting to put a little 2 in there. It is Ag2SO4. And for this one, there's 1 mole of sulfate ions for every 1 mole of silver sulfate. Convert that to molarity as well. And I have 0.014 moles, a molar sulfate ions. Calculate your reaction coefficient, QC. If I look at this, these two are aqueous, this is a solid. So I'm going to have the concentration of silver, quantity squared, times the concentration of SO4 2 minus, raised to the first power, 0.028, quantity squared, 0.014, gives me 1.1 times 10 to the negative 5th for the QC value. QC is equal to KC, so this solution is at equilibrium. No more solute will actually dissolve.